All right. Uh, Hello, everyone. Welcome to today's coaching seminar. It's my pleasure to introduce Éric Delaygue from Camille Jordan, Lyon. And he'll tell us about Abel's problem, Gauss, and Cartier congruences.
Okay, so thank you very much for the invitation. It's a joint work with Tanguy Rivoal from Grenoble. And so the structure is the following. I will first motivate this work by Golich's prediction in some hypergeometric setting, which was a conjecture that we solved with Tanguy Rivoal. And it is linked to what is called Abel's problem. So I will then talk about some generalities about this problem from an analytic point of view and algebraic point of view. And then I will give an arithmetic characterization, which turned out to be really handy in the hypergeometric setting. So we then go back to Golich's prediction and prove this conjecture. And if time permits, I will try to give some example beyond the hypergeometric case. Okay. So first, some motivation with the prediction by Goichev. Okay. So I will recall what are generalized hypergeometric series. So if you take parameters, alpha and beta, which are rational, but you have to avoid non-positive integer. And you take the generating series of a ratio of what is called the Poramer symbol, which generalizes factorial, okay, or sometimes called the rising factorial, and which is defined below. And then you have some example. If you take, for example, R and S equal to 1, you take at the numerator any rational number alpha, and at the denominator you take beta equal to 1, and then you have an algebraic function. Okay. Another example, take 1/2 at the numerator and 2 ones at the denominator. Then you have this elliptic integral, and it is known to be transcendental. Okay. And then an exotic example from Rodriguez-Villegas. You can make a suitable choice of the parameter alpha and beta together with a good choice of rational constant C. And if you rescale the corresponding generalized hypergeometric series, then it becomes a generating series of a ratio of factorial, which it is given parameters. And it turns out that it is algebraic with a huge degree. Okay. And this ratio factorial was in fact used by Chebyshev in his approximation of P of n. Okay, so now we will look more precisely at what we called factorial hypergeometric series, as in the last example. So we shall say that an hypergeometric series is factorial if we can rescale it so that it becomes a generating series of ratio of factorial. So, okay, at the beginning, you have just ratio of paramers, but now you want a ratio of factorials with some integer, positive integers, the E and F. Okay. So you have a combinatorial criterion to decide when you can, in fact, do such rescaling, okay? And you can prove that your hypergeometric series is factorial if and only if you take this rational fraction. So as you see, the alpha which were in the parameter symbol are still at the numerator and the beta at the denominator. And you want this to be a rational fraction with coefficient in Q. This means that, in fact, you have a lot of symmetries between the alpha is, okay, and also a lot of symmetries between the beta is, in some sense that, in fact, if you have 1/3, for example, that appears as the numerator, as one of the alpha, then you must have also 2/3. Okay, and similarly, if you have 1/5, you will have 2, 3, and 4/5 that must appear also. So it's kind of this kind of symmetry. Okay. An example. So with the transcendental hypergeometric series, this one, you can rescale it and replace x by 16x, and then you have in fact the generating series of factorial ratio. Okay. So what are Goye's predictions? It is in a great paper by Zagier on the arithmetic of differential equations, where Zagier states his prediction of Goye's, and it was inspired by the theory of motifs. So the prediction is the following. You take an hypergeometric series, which is both algebraic, but also factorial. Okay. Then, so we will see later with some analytic observation, you have in fact to consider x times eta as the algebraic factorial hypergeometric function, okay? And then the equation is just in terms of eta, okay? So being given this, the conjecture is that you have a non-trivial algebraic solution to the equation y prime is equal to eta y. But you have more. You have, in fact, that y is in the field generated by x and eta. Okay. So, in other words, if now you consider the generating series of factorial ratio, like on the previous slide, and you assume that this generating series is algebraic, okay? Then if you compute a non-trivial solution, you will have exponential of the antiderivative, okay? And it just says that this is algebraic, and even more that in fact, it is in the same field as the one generated by x and f, okay? So just a remark there is that in fact, you have also a way to decide whether a given hypermetric series is algebraic or not, okay? At least when the parameters do not differ by integers. And it is a theorem by Buckers and Ekman. Okay, so you can also transfer this when you have a factorial hypergeometric function. Okay. So stop me if you have a question. So in the same paper, Zagier proves the first part. So the fact that you have a non-trivial algebraic solution to the first order equation, okay, of the prediction of Golychev, if the factorial ratio are of the following form, so binomial coefficients, and the two sporadic ones, okay? And it was done by explicit computations. And the goal of this presentation is to give some hints on how we prove with Tanguy-Rivoal that the conjecture holds, but in fact that it was sharp. So if you take again x times eta x to be an algebraic hypergeometric function, here you don't ask the hypergeometric function to be factorial, okay? Then in fact you have an equivalence that you have an algebraic solution to the first order equation, if and only if, in fact, your hypergeometric function was factorial. Okay, and we will see that we managed to prove this by looking at arithmetic properties, in fact, of the differential equation, because it is easy to compute some arithmetic invariant of hypergeometric series. We'll see later. So some generalities first on Abel's problem, which correspond to, in fact, the equation y prime is equal to eta y with eta algebraic. Okay. So it appears when one wants to detect if all solutions of a linear differential equation are algebraic. Okay. So we consider a linear differential equation of order n. Okay. So with coefficient, rational fraction, with coefficient in the number field k. You have something which is called the Riccati equation. This is a nonlinear differential equation of order n-1, so that in fact, you have a non-zero solution to the original equation Ly equals 0, if and only if you have a solution of the Riccati equation, which is the logarithmic derivative, okay, of y. And if you know that your original operator is irreducible, then the associated equation has a full basis of algebraic solution, if and only if the Riccati equation have an algebraic solution, which is the logarithmic derivative of an algebraic function y. So you search for a solution of the Riccati equation, which satisfy y prime is equal to eta y with the y algebraic, okay? And this last part is what is called Abel's problem. And it was already known by Boulanger and Pellevé, okay? So if you have the following question, when does an equation, linear differential equation, have a full basis of algebraic solution? Then you can reduce the problem to 3 steps that can be solved in a finite number of steps. So first one, you need L to be irreducible to apply the result on the previous slide. So you have a way to reduce to the case where L is irreducible, okay? And it was done by Singer. Then you want to detect if the Riccati equation have an algebraic solution or not, okay? And again, you have a way to do this in a finite number of steps, which was designed by Singer. Then, if you know that you have an algebraic solution of the Riccati equation, you want to know if the first order equation y prime is equal to eta y also admits a non-zero algebraic solution, okay? And there you have an algorithmic way to decide this, one which was designed by Rich, and another one 10 years later by Baldassari and Dwork. And I will discuss the one of Baldassari and Dwork later. Okay, and the third step is called Abel's problem. Okay. So first, if you take this problem of Abel, you have so you start with eta algebraic and you ask yourself if there is a non-zero algebraic solution, okay, to the first order equation. You have first analytic observation using Puiseux expansion. So I recall the theorem of Newton and Puiseux, okay, that if you start with an algebraic function y and you take a point delta in P1, then in fact, y admits a convergent Puiseux expansion in a slit disk of center delta, which means that if delta is finite, you have the first expansion, okay? And if it is infinite, the expansion is slightly different, okay? And the point here is that, in fact, R could be negative, okay? And you expand the series in the different roots of x, okay? Or of x minus delta, okay? And it is convergent, okay? So when you know this, in fact, already you can apply this, for example, at the origin. And if you know that you search for an algebraic solution y, so your function eta will be the logarithmic derivative of y. And in fact, you have a specific expansion. So like this, when in fact it starts with a power of x to the minus 1, okay? So you can stick to this case because otherwise you will not have algebraic solution. Okay. So now an algebraic characterization. So again, we consider this equation. Then you can prove that y is algebraic, okay, if and only if you have a positive integer m, such that m times eta is the logarithmic derivative of an element of the field generated by x and eta. Okay, so how to do that? So the if part is that if you know that you have such an integer and so that m eta is equal to nu prime over nu, in fact, you can just check that the solution is given by a constant times mu to the 1 over m, okay? And it works well. So the only if part is that if you know that y is algebraic, so you consider the minimal equation of y over the field generated by x and eta, and you will differentiate this minimal equation. And since y is of order 1 in this field, okay, y prime is eta times y, you will have another equation of the same order. And so you will do some compensation to try to cancel the maximum order. You have an equation of order 1 less at minimum. And so in fact, everything vanish, and you've at the end, you manage to prove that you have some integer m, such that m times eta is nu prime over nu. Okay, so this is just the way to do this. But in fact, doing this, you can do a bit more, and you can show that if y is algebraic, then its minimal equation is of the form y to the m, the same m, okay, plus mu equals 0 for, again, some mu in the field k x eta, okay? And so you see now that if you remind the Goldilocks prediction, you have two parts. The first is that you have an algebraic solution to the first order equation. But the second one was that you hope that, in fact, this solution is in the field generated by x and eta. And you see that at this point, with the algebraic characterization, so first you want to ensure that you have such an integer m, but in fact, regarding the Goldilocks prediction, you want to prove that m is equal to 1. Okay. So Baldasseri and Dwar give an algorithm to detect if such an m exists. Okay, and it was by means of geometric consideration on the curve associated with eta. Okay. Okay. So the problem is that this characterization, algebraic characterization, was not practical, for example, in the hypergeometric situation, because hypergeometric functions have a lot of parameters, and the situation changes when the parameter varies. Okay, so now we will look at an arithmetic characterization. So I fix a number field k, which is Galois over q. Okay, and as we explained before, we know that we can restrict ourselves to eta, which starts with something like a over x. Okay, but now we just look at the case of Lorentz series. So it's not the full generality of Puiseux series, but in fact you can then transfer all these results to Puiseux series. Okay, so we start with Lorentz series, which is algebraic of this form eta. Okay, so sorry, I will recall the notion of P curvature. So here, the notation, we take a prime ideal P, which is above a rational prime, okay, little p, of good prediction. What this means that since you know that eta is algebraic, you have a theorem of Eisenstein, which tells you that, in fact, you can, for almost all prime p, reduce eta, the coefficient of eta modulo p. Okay, so they are in the localization at p of the integer of k. Okay, so doing this, now you name kp the residue field of k at p. Okay, and you have eta, which belongs to this field of Lorentz series. And then you consider the map, delta p, which sends any Lorentz series with coefficient in kp y to this Lorentz series, to which we apply p times the operator delta minus eta. Okay, so usually doing this, it is easy to see that the constant modulo p are the Lorentz series in the variable x to dp, not x, okay, x to dp. So it is easy to see that, in fact, this is Kp x to the p linear. But in this precise situation, it turns out that if you do calculation, this map is Kpx linear. Okay, and this is really the observation which is really helpful with the P curvature. Okay, so doing this, you have this theorem, which is the easy part is due to Eisenstein, and the difficult one is by the Chinosky brothers. So you have an equivalence between the three assertions. So the first is the Abel's problem. Okay, you have a non-zero algebraic solution to this first order equation. Second one, in fact, you have A0, which must be a rational number. Okay, and if you look at the non-trivial solution, so exponential of an antiderivative of eta, then you have an integrality statement that is the Taylor coefficient do not have denominator in a finite. They just have denominator in a finite set of prime integrals. Okay, so here OKS stands for the localization of the ring of integer of k at S. Okay, so this means that it has only denominator in a finite set of prime ideals. Okay, so the third condition is about the P curvature, that for almost all prime ideals of k, the P curvature vanishes. Okay, so you go from 1 to 2 by the Eisenstein theorem. Okay, then 2 implies 3 is quite easy. It's just really easy differential algebra. And the difficult part is to show that 3 implies 1, which is in fact the solution of the Grothendieck-Cass conjecture in rank 1 by the Chinosky brothers. Okay. So just a remark that we will see in the next slide is that, as I said, the point 2 is something about integrality. Okay, we just want to prove that for almost all primes, you don't have this prime at the denominator of exponential of the antiderivative of eta, while in fact 3 is more a result about differential algebra. Okay, okay. So now we have this difficult theorem in hand, so the one of the Chinoskys, and we want to traduce it in something which is indeed to apply things to hypergeometric series. So we will translate this in congruencies. So first things is to go from this theorem to Cartier congruencies. So here I stick to the case where the number field is equal to Q to avoid some ramification and Frobenius consideration. Okay, and so to have nicer congruencies. So here the key result is that, so now your algebraic function has coefficient in Q. So now you are searching for prime of good reduction. So Eisenstein theorem says that for almost all primes P, you can reduce your algebraic series. Okay, and then in fact, so previously we saw that the P curvature is Q of X linear. So in fact, you're just interested in the value of the P curvature at 1. Okay, since in fact, if you say that the P curvature vanish, it is equivalent to say that delta P of 1 is 0 mod P. Okay, and here you have this nice result of Jacobson, which says that delta P of 1, you can compute this in terms of eta. So it is minus eta as the P minus 1's derivative of eta plus minus eta to the P, and this is mod P. Okay. Now we will call such congruencies Cartier congruencies. So we call this with Tanguy-Riwal because in fact, you have several classical congruencies that have already a name, like Dworke, Lucas, or Gauss congruencies. Okay, And this kind of congruence, we saw them in many papers in the literature, but they don't have names, so it was not really handy. And the fact is that, in fact, it exactly corresponds to the fact that the sequence A of n is fixed by some Cartier operators. Okay, so we call them Cartier congruences. Okay, so let's say we have a generating series of the AN, and the congruences are the following: A of np is congruent to AN mod p. Okay. Then the point is that, in fact, the Jacobson formula, if you say that delta p of 1 is equal to 0, it will exactly translate in the fact that the coefficient of the algebraic function eta has Cartier congruences. Okay, so it was shown by Boston that you have. So in fact, you have an equivalence for each p. But I just write this for almost all p, but it is okay for each p is independent. So. But in fact, you have this equivalence. So the P curvature vanish for almost all P if and only if you have Cartier congruences for X eta X. Okay. Is there any question? Okay. So this is the first reformulation. Now, second one about Gauss congruences is the one when you want to reformulate the integrality statement. Okay, so it's more p-adic. Okay. So here you want to use something which is really practical when you study exponential from a p-adic point of view. This is the Dieudonné-Douarc lemma. And so you start with a power series, which has no constant term, and you fix prime number p. Okay. Then you have an equivalence between the exponential of s has no p in its denominator. Okay. And you have this that s of x to the p minus p times s of x is in fact divisible by p. Okay. Now we consider what is called Gauss congruences. So this is the same thing as Cartier congruences. The difference is the n that you can see in purple. Okay, and it's quite different because Cartier congruences, this is just mod p. So you have just p-adic variation eventually 1 when you take the difference of a on p and an. But here you see that in fact the congruences can be with higher powers of p when n is itself divisible by p. Okay, so it is much general that Cartier congruences. So if you have Gauss congruences, you have Cartier congruences. Okay. And then you can prove the following equivalence. So the integrality statement in the theorem of the Chinosky, you can reformulate in terms of Gauss congruences for almost all p. Okay, you have this equivalence. And here you have a finite set S of primes. Okay. Okay, so now we have reformulated all the statement in terms of congruences. And then you can obtain a characterization via congruences. Okay, so still we consider, so now I state the result with a number feed because it is the most general result. Okay, so just to know that you can in fact apply this to every algebraic function over Q bar. Okay. But I did not define those congruences in number feeds. Okay, but okay, it's quite similar. So the equivalence is the following: that now you have an algebraic solution to the first order equation. Okay, if and only if you have Gauss congruences for almost all p, and if you have Cartier congruences for almost all p. One thing this is funny that in fact. You see that Cartier congruences are weaker than Gauss congruences, but for an algebraic function, when you have this for almost all p, then this is equivalent. Okay, it's not equivalent for a fixed p, but for almost all p, if you have weak congruences, so you have strong congruences. Okay, so you can readily extend this equivalence to the case. Here we work on Laurent series. Okay. But you can extend this to the case where eta is plus a series. So you can do all of this in the most general case, the most arithmetical general case. Okay. One thing that is funny that you see that in fact the condition 1 in the equivalence does not depend on the base point, okay? But 2 and 3 depend because we define everything in terms of the expansion at 0 of eta, okay? So you can ask yourself, okay, but if I expand it at another point, what happens? But what is funny is that you can prove that in fact, since you have 1, the congruencies does not depend on the base point, okay? So you can reformulate like this, that in fact, if you expand at such at a point delta 1 and at a point delta 2, then you have Gauss congruencies for almost all p at delta 1, if and only if you have also at delta 2. Okay. So now back to Golic's prediction. So how to apply this to the hypergeometric settings? So it is possible to prove that if you take an hypergeometric series which is globally bounded, so it means that it has positive radius of convergence, but also you can rescale the hypergeometric series so that you have integer coefficients. So it is really reminiscent of the conclusion of the Eisenstein's theorem. Okay. So if this is globally bounded, then you can prove the following: that your hypergeometric series is factorial if and only if it has Gauss congruencies for almost all p, and if and only if it has Cartier congruencies for almost all p. And I will give a short sketch of this later. Okay. So proving this, but you see that then you can prove Golic's prediction because, as I said, algebraic series are globally bounded. Okay. And so with the reformulation of the theorem of the Szynovsky in terms of congruencies, you obtain the first part of Golic's prediction. Okay. So how to prove this? Just a sketch of the proof. So I start with a generalized hypergeometric series, which is non-polynomial and globally bounded. And I write is Taylor coefficient at 0, like a ratio of parameter symbol, like this, okay? And I write D for the least common denominator of the parameters, alpha and beta. Okay. Then in fact, you can always prove the following congruence. So this is an almost Cartier congruence for large P. So if P is large enough in terms of D, okay. So I think that if P is greater than D, it works already. For every non-negative integer n, you have this congruency. So if you look at this, you can see that if you erase what is purple, in fact, this is exactly Cartier congruencies, okay? But you have this twist by the purple things there. And so K has to be defined in terms of P. So this is the inverse of P modulo D, okay? And then you have this bracket of X is the fractional part of X. But if X is an integer, it is equal to 1, okay? So you have some twist. You have almost Cartier congruencies, but you can prove this in the wide generality of globally bounded hypergeometric series, okay? So now, if we take an example, you take parameter one third at the numerator and 1/2 1 at the denominator. You fix P to be 11. Then you compute D is 6, okay? And you compute that P is 5 modulo 6, okay? So now you can see that the inverse of P modulo 6 is still 5, okay? And you obtain such a congruence. So almost Cartier, so you not have 1/3, you have 2/3 in the right-hand term, okay? So what does it mean? I just recall the general congruence, which is the same thing that on the previous slide. So what does it mean? That in fact, the hypergeometric series has Cartier congruencies. You can prove that in fact, it is if and only if the twist of the alpha is equal to alpha, okay? And this for every k coprime to D. And with this in hand, you can prove that it is equivalent. It forces too much symmetry on the alpha, and it is equivalent for f alpha to be factorial. Okay. So, okay. I don't. I have time or not to?
Yeah, you still have time. Yeah.
Okay. So, so we saw that in fact the arithmetic characterization is efficient in the hypergeometric world, but the hypergeometric world is quite easy to do some congruencies. Okay. So now some non-hypergeometric congruencies. So two situations where you have such congruencies. The first one is inspired by work of Kontsevich and Cassel and Rothenauer. When you take a square matrix A with entries in the free group algebra, so Q, where here the variables so do not commute. Okay, they do not commute. And what you do, you take then power of the matrix A. So you have another matrix with complicated term. You take the trace of this and then the constant term. So you just look at the term, the coefficient of 1, okay, in all of this. So you have a number, okay, and you take the generating series, which is GA of X. Then Kontsevich prove this when the matrix is a scalar matrix A, okay, and Cassel-Rothenauer proves the general case. Then both the series GA and this exponential are algebraic, and as you see, this exponential is in fact a solution to Abel's problem. Okay. So you can prove similar things for in the commutative world. Okay. So now what you do, you take a square matrix with entry Laurent polynomials. Okay, over a number feed. So here the variable commute. You do the same construction, okay? And you can prove that in fact, these things has always Cartier congruencies for almost all P. Okay. So it's not that hard to prove this. It's quite easy. So in consequence, you obtain that in fact, the same series, so G of A and the solution of the Abel's problem are, if you apply the previous criterion, they are either both algebraic or both transcendental. Okay. And so it was first situation where when such congruencies appear. And another one, which is quite general, it is related to what is called Dot sequences or realizable sequences, okay? And it is also so related in Mazur zeta function. The context is quite general. You take just X to be a set and F map from X to X, okay? And so the only assumption is that in fact you assume that the fixed point of F to the N is always finite. Okay. So doing this, you can prove, so it was hard to be sure of, to prove the good reference for this, but it's really old, okay? And so you can prove that the generating series of the number of fixed point of F to the N, okay, in fact has always Gauss congruencies for every prime P. So not just Cartier mod P, even Gauss congruencies, which are stronger congruencies. You can always prove this, okay, while looking at the orbit of F and things like this. Okay, so doing this, if you consider the solution of the Abel's problem, which now this is called the Artin-Mazur zeta function in dynamical system associated with F. You have this. It has the rational coefficient, okay? And you see that if you apply the criterion, that in fact, you have again that both the generating series GF and ZF are either both algebraic or both transcendental. Okay. And thank you for your attention.
Thank you for your talk. Are there any questions? Yes, so there's a question. So does one have Cartier congruences in the case of Kontasevich?
In the case of Kontasevich, you have, I think, yeah, because since both are algebraic and you have still the differential equation. So by the criterion, you must have Cartier congruences, yeah.
Any other questions for Eric? Can you say a little bit more about, you explained the case where K was the rational numbers. When it's not, so it's a general number field. So is it much more difficult or?
No, it's not that hard. The problem is just you want to define congruencies for just unramified prime, okay? And doing this, you have a unicity of Frobenius. And then what you ask is that A of np is not congruent to A of n, but is congruent to the Frobenius of an. Just this, okay? It's why when you now stick to Q, the Frobenius disappear, okay? But the proof is not everything generalized well. Okay.
Any other questions for Eric? Okay, I think we don't have any questions. Thank you so much, Eric, again for your great talk.
Yeah, thank you. Bye.